Welcome to today's Explainer, where we are going to completely transform the way you approach your Cambridge physics examinations, specifically looking at syllabus code 0625. I want you to picture a symphony conductor for a second. A master conductor doesn't just throw every single instrument at the audience all at once, right? That would be chaos. They orchestrate the sound. They know exactly when the strings should swell, when the brass should cut through, and when there should be absolute silence. Well, when you sit down for your physics exam, you need to be that exact same conductor. Your arguments, your data, your formulas, each paragraph you write should be an instrument playing in perfect harmony. Today, we are going to master the examiner's playbook by looking through the lens of an incredibly critical topic: evaporation and cooling. To set the stage, let's imagine two types of students. Let's call them Alex and Sam, whose answers we constantly see in examiner reports. Alex is the overloader. Alex panics and just throws raw physics facts at the page, defining everything under the sun but providing absolutely no analysis. Then you have Sam. Sam is the rusher. Sam completely misses the specific requirements of the command words and just writes down the first thing that comes to mind. Both of these approaches are going to bleed marks. Today, we are going to look at exactly why these answers fall flat. We'll correct them together, and I'll show you how to orchestrate a true masterpiece that scores maximum marks every single time.
What is absolutely fascinating to me is the sheer weight of the topic we are dealing with today. You might look at the topic of evaporation and think, oh, it's just a minor foundational concept, maybe worth a couple of points. But the reality is that the core principles of evaporation, cooling, and the related thermal physics phenomena can account for up to 15% of the total marks in your examination. 15%! To put that into perspective, this fundamental topic alone represents the difference between two entire grade boundaries. This is exactly what we call the 15% trap. Many students, like our friend Sam the rusher, breeze through these questions thinking they're easy, surface-level marks. On the flip side, students like Alex write an entire novel and waste precious time because they don't know what the examiner actually wants to see on the page. We are going to make sure you capture every single one of those percentage points by combining your solid physics knowledge with a razor-sharp exam strategy. You aren't just going to know the physics, you're going to know exactly how to play the game.
So, here is our roadmap for today's session. First, we'll dive deeper into the 15% trap. Then, the physics of the energetic escape. Third, boiling versus evaporation. Fourth, accelerating evaporation. And finally, the ultimate examiner's playbook.
Section 1. The 15% trap. Let's uncover exactly why so many capable, smart students fall into this massive pitfall. It happens because thermal physics questions, particularly around evaporation, often look deceptively simple. When a past paper asks you to explain why a sweating athlete cools down in a breeze, a weak answer might go off on a tangent detailing the biological function of sweat glands, mixed with some scattered random physics terms. That completely loses the thread. Another answer might just say, well, the wind blows the heat away, which earns exactly 0 marks from a Cambridge examiner. The trap is fundamentally underestimating the incredible precision required by the syllabus. The crucial point here is understanding the 3 main cognitive domains being tested: knowledge and understanding, application, and analysis. Look, it's one thing to memorize the definition of evaporation. That covers your knowledge domain, sure. But when the exam paper asks you to apply that concept to a completely unfamiliar context, like a complex industrial cooling tower or an unglazed clay water pot in the middle of a hot desert, that is where application and analysis come in. Students find applying concepts to unfamiliar context incredibly difficult because they lack a structural framework. Having that framework is exactly what separates the top-tier A-star candidates from the rest of the pack. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 2. The physics of energetic escape. To avoid the common mistakes highlighted by examiners, we absolutely need to utilize a proven structural framework.
The absolute best framework for Cambridge physics written answers is something we call PEAL. That stands for Point, Evidence, Explanation, Link. When you are asked to describe the mechanism of evaporation, you do not just dump facts like Alex does. You make a clear point, you provide physical evidence, you explain the mechanism using proper terminology, and you link it right back to the specific question asked. Let's look at the actual physics. Evaporation is defined specifically by the syllabus as the escape of energetic particles from a liquid surface. I highly recommend using a visual story method to really encode this into your memory. I want you to picture a massively crowded room. That room is your liquid. Most people in the room are just mingling, moving at a totally normal, average pace. But a few individuals in that room are incredibly energetic. They're practically bouncing off the walls. These represent your high-energy particles. When these energetic people reach the door, which represents the surface of the liquid, they have enough kinetic energy to break free from the attractive forces of the crowd and escape outside into the air. If your answer doesn't explicitly mention that it is the most energetic particles, and if you fail to specify that this escape only happens at the surface, you are leaving guaranteed marks on the table. The examiner is actively hunting for those two specific phrases.
Now, let's take that analogy a step further. What actually happens to the mood of the crowd when the most energetic, hyperactive people leave the room? The overall energy of the room drops, right? This is the exact mechanism behind the cooling effect of evaporation. Because only the particles with the absolute highest kinetic energy manage to overcome the intermolecular forces and escape, the average kinetic energy of the particles left behind in the liquid decreases. And since temperature is literally just a macroscopic measure of average kinetic energy, the temperature of the liquid falls. Let's watch a real-time transformation here. A weak, flawed, past paper answer might read something like, the water gets cold because the hot parts leave and go into the air, making the water left over less hot. Ouch. Let's rewrite this live using our Peel framework. Your point, evaporation causes cooling. Your evidence and explanation, the most energetic molecules escape the liquid surface, meaning the average kinetic energy of the remaining molecules decreases. Your link, a decrease in average kinetic energy results in a lower temperature of the bulk liquid. Suddenly, we have gone from a red pen disaster to a green checkmark masterpiece. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3. Boiling versus evaporation. Let's pivot to a stark contrast that examiners absolutely love to test year after year.
This is an area where we consistently see students stumble, mostly because they completely fail to evaluate the command words in the prompt. If a question asks you to compare the two processes, simply listing facts about boiling and then completely ignoring evaporation misses the analytical requirement entirely. Comparing requires a structured approach where you look at both sides of the coin simultaneously. What's really interesting is the technique required to properly communicate these facts to the examiner. They literally require you to use comparative connectives to support each comparison with evidence. You cannot just write two separate, disconnected paragraphs. You must orchestrate them into a single cohesive argument. For example, a top-tier student would write, evaporation occurs only at the surface of the liquid, whereas boiling occurs throughout the entire body of the liquid. Furthermore, evaporation can take place at any temperature, while boiling only occurs at a specific, fixed temperature known as the boiling point. Do you see what happened there? By using comparative connectives like whereas and while, you are signaling to the examiner that you are actively analyzing the relationship between the two concepts, not just blindly reciting memorized facts from a textbook. This is exactly how you demonstrate the higher-order evaluative thinking that Cambridge demands.
Section 4. Accelerating the evaporation process. Let's look at the specific variables that change the outcomes and get ready for a highly interactive workshop segment.
The syllabus defines 3 main factors affecting the rate of evaporation: temperature, surface area, and air movement. Let's do a quick mental workshop right now. First, our data scan challenge. Imagine you have a complex data table in front of you showing a dramatic increase in evaporation rate as surface area expands. You have 60 seconds to extract the trend. What's happening? The core trend you need to extract and articulate is that a larger surface area exposes significantly more particles to the boundary, increasing the statistical probability of an energetic escape. Next challenge, find the flaw. Imagine you read a student's answer that says, a fan cools you down because it makes the air colder. Spot the massive flaw? The examiner commentary on this would be brutal. They would clearly state that the fan does absolutely nothing to change the air temperature. What it actually does is remove the humid, saturated air sitting right near the surface of the liquid, maintaining a very steep concentration gradient so that more particles can continue to escape. Finally, our speed writing challenge. If you had just 30 seconds to write a perfect Peel paragraph on the effective temperature, your structure should instantly snap into place. You'd say, higher temperature means higher average kinetic energy, resulting in a much greater proportion of particles possessing the required activation energy to break those intermolecular forces and escape the surface. Boom. That is how you synthesize physics concepts under intense time pressure. Section 5. The Examiner's Playbook. The most crucial point of this entire explainer is pivoting from just knowing the physics to exactly how to write about it.
To secure maximum marks, you absolutely must adopt a strict problem-solving framework.
Whenever you face a multi-part physics question, especially on thermal transfer, you first deconstruct the given information. Literally take your pen and highlight the knowns and the unknowns in the prompt. Next, you solve systematically. Break the physics down into logical, bite-sized steps. Do not just jump straight to the conclusion in your head. Finally, evaluate and check. Does your answer actually make physical sense in the real world? If you calculate that a cup of coffee cools down to -50 degrees Celsius in a normal room, you need to evaluate your process and realize you've made a terrible mistake somewhere. Your presentation of this information must follow strict conventions. Use proper headings, correct scientific terminology, and clear annotations.
This brings us to what is arguably the single most vital exam survival technique of all, the method mark strategy. In Cambridge Physics, marks are heavily weighted toward the process, not just the final numerical answer at the bottom of the page. If you orchestrate your arguments clearly, showing your formulas, clearly writing out your substitutions, and detailing your logical reasoning, you are building an incredible safety net for yourself. The syllabus explicitly prioritizes analytical depth. By laying out your systematic analysis step by step, you are proving to the examiner beyond a shadow of a doubt that you understand the fundamental mechanics of the physics. And here's the best part, you prove this even if your calculator finger slips at the very last second and you get the final number wrong. The method is everything.
This builds perfectly into the harsh reality of exam day. Let's look at the top 3 examiner warnings pulled straight from the official Cambridge Principal Examiner reports. Mistake number 1 is forgetting the proper format, leaving out your standard units, or failing to explicitly show the formula you are using before you plug the numbers in. Mistake number 2 is failing to check your presentation. Look, if your handwriting or your mathematical layout is a chaotic scribbled mess, the examiner literally cannot follow your logic to award you those precious method marks. They aren't going to guess what you meant. And mistake number 3, which is incredibly common, is providing answers that are not specific to the context given in the question. If the exam question is specifically about evaporation from a green leaf in the sun, do not talk generally about boiling water in a kitchen kettle. Tailor your terminology directly and specifically to the scenario they provided.
This, right here, is a direct, high-impact alert from the examiners themselves. I need you to listen very closely to this quote. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. Remember this always. Your working out on that page is your direct line of communication with the examiner. It is your absolute proof of competency. Do not hide it.
As we wrap up this explainer on evaporation, cooling, and the overarching strategy for your Cambridge Physics exams, I want to leave you with this final, provocative thought. When you sit down in that exam hall and that clock starts ticking down, will you just throw random notes at the page hoping something sticks, or will you step up to the podium and conduct your answers with absolute precision and clarity? Will you rely on just a rushed, panicked final answer, or will you systematically orchestrate your method marks to guarantee your success? Take the examiner's playbook we've discussed today, apply the Peel framework to your paragraphs, decode those command words meticulously, and go ace that exam. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Keep learning, keep structuring your knowledge, and I look forward to exploring our next topic with you.